pentagonal bipyramidal. Anyone wants to join? Okay, in associative mechanism, you can see here in initial concentration, there are two reactants in the initial concentration, and the first step is the slowest step. So you can consider the first step, the slowest step is just like the rate determining step. So it will be a second order reactions. You can see here, and in this reaction, the rate will be depends upon the initial concentration also and the concentration of incoming ligands also. But in SN1 mechanism or dissociative mechanism, the rate will only depends upon the initial concentration. So it is the difference in between dissociative and associative mechanism. In dissociative mechanism, the rate depends upon the initial concentration only. But in associative mechanism, the rate will depends upon the initial concentration as well as the concentration of incoming ligand. There will be another mechanism. This is called interchange mechanism. In interchange mechanism, there will be no formation of intermediate. It will just pass through a transition state or activated complex pathway. Okay, you can see here in the first step, they will form an activated complex. Further, the activated complex, it leads to the formation of a product and along with the leaving group. Further, this interchange mechanism, it will also divided into two types. One will be interchange dissociative mechanism, ID, and another will be interchange associative mechanism, IA. So what is the difference in between ID and IA? ID says that the MY bond begins to form before the MX bond is fully broken. That means he's saying that the 90% part of the MX bond is already broken. Only 10% part is remain to remove from the group, and this in this condition the MY bond starts to form. This is called, but the major part is that already 90% part of the MX bond is already broken. Particularly few part of the MX bond, it will be make a interaction with the metal complex, but is going to be removed from the complex. At that point, the MY bond begins to form. That's why the major part is the breaking part. That's why this is called the dissociative, interchange dissociative mechanism. Similarly, in interchange associative mechanism, you can check here. The MX bond begins to break before the MY bond is fully formed. That means in associative mechanism, the bond formation process starts initially. That means 90% part of the MY bond starts to make a formation of a new bond with the metal complex. After the 90% formation of MY bond, the MX bond begins to break from the complex. That means the majority part is the bond forming part, the MI bond formation. That's why this is called interchange associative mechanism or IA. So it is simple. You can understand just like that. Which part will be the dominant part, which one part is the less dominant part. Okay. So we need to read down all these things in your in also you can follow your study material in the e-Gano course, but it's the simple language. You can find out these things, you can easily understand. Okay, and this reaction coordinate path of the dissociative mechanism is just like that. This will be the energy of the reactant, and this will be the energy of the transition state 1. And this part represents the position of the intermediate. And this part will be the energy of the transition state 2. And this will be the energy of the product. So particularly you need to remember this part will be the important part. This will be the intermediate energy position, potential energy position of the intermediate. So when in a reaction pathway, there will be a formation of this type of structure. We can predict that this one will be the intermediate position. Okay. The similar things are written in this here also. You can read out also. And this is a two-step mechanism. First one will be the slow one, second one will be the fast one, and slow one will be the rate determining step. And this is the representation of associative mechanism. Associative mechanism also similarly follows a similar pathway. This will be the position of the intermediate. Okay. In associative mechanism, there will be two types of intermediate structure. One will be capped octahedral, another will be pentagonal bipyramidal. So capped octahedral means nothing. This is the octahedral wedge intermediate. And this is the interchange mechanism. One will be ID mechanism, another will be IEA mechanism. Let's we are going to discuss about another concept, lability and inordinate of the transition metal complex. So particularly in a reaction, there will be chances of formation of two types of products. One will be thermodynamic product, another will be kinetical product. In your third year course or plus three or BSc third year final year course, there these two terms are also important. You may know one will be thermodynamic stability, another will be kinetic stability. Thermodynamic stability, the product will be energetically more stable. It may take a longer time to form, or it may take a little bit lower time to form, but the product energy will be much more higher. And I can say the metal ligand bond strength in a thermodynamical product, it will be very, very stronger. But in kinetical product, it can form in a certain way. Certain way means it will form within a certain period of time, or it will form within a less time. Particularly, if the half-life period, it will be less than T half. T half, it will be less than half. Then this product will be called just like a kinetical product. If the half-life period will be more than half second, then the product will called as a thermodynamically stable product. So on the basis of kinetic stability, we can divide the products into two types. One will be lability, another will be inertness. Labile means the product which we can get in a faster way, or we can get it within a shorter time. And inert product means we can get the product by taking a long time. Okay, so inert means just like you can consider the product is a stable product, and we cannot further react with another complex or another ligands. And labile means it can further react with another ligand, it can give another product, just like that. Okay, so on the basis of valency bond theory, and we can divide the complexes into two types. One will be labile product, another will be inert product. So on the basis of valence band theory, the octahedral complexes we can divide it into two types. One will be outer orbital complex, another will be inner orbital complex. Outer orbital complex, particularly those complexes having the D2 sp3 D2 hybridization, and inner orbital complexes are the complexes having the hybridization D2 sp3. The difference between outer orbital and inner orbital complex is that in outer complex, the utilization and the d orbitals are, particularly the outer d orbitals are utilized, and in inner orbital complex, particularly the inner d orbitals are participate in the hybridization. Suppose I can say the fast throw transition series, particularly some chromium complex. So when we'll form a chromium complex, chromium water 6, just like, then the d orbitals that are participate in hybridization are the inner 3d orbitals. Okay, if you consider the second row transition series or the third row transition series, you can utilize the outer d orbitals, just like 4d, 5d. So if the utilized d orbitals are the inner d orbitals, we can say this is d2sp3. If the utilized d orbitals are the outer d orbitals, we can say sp3d2. You can see here in vanadium complex, vanadium hexaamine 3 plus, we can see is using the 3d orbitals in hybridization. So here the hybridization will be D2sp3 hybridization. This will be a inner orbital complex. But in MnCl63 plus manganese hexachloride, you can see here is utilizing the outer d orbitals, because the inner d orbitals are not available for the hybridization. Okay, so here the d orbital is 4d. This one will be the 4d orbital. This one will be the 3d orbital. So when a complex utilizing its inner d orbitals for formation of hybridization, we can say this will be inner orbital complex, and this one will be outer orbital complex. So according to VBT, he is saying that the inner orbital complex will be stronger because it is utilizing the inner d orbitals, and the outer orbital complex will be and the labile one, because it is utilizing the high energy orbitals or the outer orbitals. You can see here The ML bond in outer orbital complexes is larger, weaker, and higher in energy, whereas the inner orbital complexes, the ML bond is shorter, stronger, and lower in energy. Okay, so according to VPT, one can consider the inner orbital complexes just like a stable complex, and it will be the inert product, and the outer orbital complexes are the high energy products, and or I can say these are the labile products. But experimentally, it is found that some of the inner orbital complexes are also labile, and some of the outer orbital complexes are also labile. And what is the exception? The exception arises due to the vacant orbitals, particularly. So you can see here in vanadium hexamine complex, the hybridization is D2sp3 hybridization. So it is utilizing the inner d orbitals for the hybridization. So the complex will be a inert complex. এই কমপ্লেক্সটা কোন হওয়া দরকার ইনট কমপ্লেক্স হওয়া দরকার but experimentally it is found that it will be a labile complex. What is the reason behind that? There will be vacant d orbital which is unoccupied by any of the electron. So this vacant orbitals it can attack by the incoming ligand, and it will get favorable for a labile complex. If the attacking of the incoming ligand is slow and the rate of the reaction is slow, we can say this will be inert complex. Okay, but actually here is a vacant orbital available for the attack of the outer orbitals. So according to postulates, it should be a inert complex, but experimentally it is found that it will be a labile complex. Similarly, you can check here chromium cyanide complex. It is utilizing the inner d orbitals, and it will be inert complex because there will be no vacant d orbital for attack of the incoming ligand to that position. You can check here manganese hexachloride complex. It is utilizing the outer d orbitals. It will be a labile complex. But the labile nature is due to not the outer d orbitals. Along with the outer d orbitals, there will be a vacant d orbital that is available for the attack of the incoming ligand. This one. Similarly, you can check here hexacyanide cobalt complex, and it is utilizing the inner d orbitals, and it will be inert complex. But some few of the exceptions are arises when there will be vacant d orbitals like this complex, this one. So later there will be a modification on the VBT, and most of the complex says lability and inertness. It will be measured by the crystal field theory. So in crystal field theory, we need to measure the energy difference in between the reactant complex and the intermediate. Suppose in a SN1 mechanism, the initial reactant complex will be a hexagonal complex or octahedral complex, and the intermediate will be just like TBB complex or square pyramidal complex. So on the formation from the reactant to square pyramidal intermediate, if the change in CFAC or crystal field stabilization energy is negative, then it will be an inert complex. If the change in CFAC in between the reactant to form a intermediate, it will be positive, then it will be a labile complex. You can see read out here. There is a change in CFAC ongoing from octahedral to square pyramidal or pentagonal pyramidal intermediate. If there is loss in CFAC, then the complex will be inert. If higher the loss of the CFAC, then more will be the inertness of the complex. If there will be no loss in CFAC, the complex will be labile or positive. Or the change in CFAC, it will be 0 or positive, the complex will be labile. Okay, and this difference in energy of or the change in CFAC is called crystal field activation energy. This is called the crystal field activation energy. If the crystal field activation energy is negative, then we can say this is a inert complex. If the crystal field activation energy is positive, we can say this will be a labile complex. Okay, you can check here a table of the complexes D0, D1, D2, D3, D4, D5. Okay, this is has been coordination number 5. That means this coordination number 5 means it represents the SN1 mechanism or SN1 complexes, SN1 intermediate. Coordination number 7 means the reaction will pass through a associative mechanism, SN2 mechanism. Here also coordination number 5 means it will pass through a SN1 mechanism. Coordination number 7 means it will pass through a associative mechanism. But most of the octahedral substitution reactions will pass through dissociative mechanism. We'll further discuss about these things. So you need to remember at least these two tables. Coordination number 5 high spin, coordination number 5 low spin. These two tables are much more important comparing to the other two. Okay, because most of the problems and numerical questions they will ask from the coordination number 5, because most of the octahedral substitution reactions they will pass through a dissociative mechanism. So you can see here when there will be D0 complex and the CFAC or CFEAE crystal field activation energy will be 0. You can check in high spin complex, in which case the positive value is high. In case of D4 and D9, the positive value is high. That means the D4 complex and the D9 complex will be the most labile complex. And you can check the numerical values, in which case the negative value is high, D8 and D3. That means D3 and D8 will be the most inert complexes comparing to other complexes. Okay. And D0 or D5 or D10, the CFE value will be always 0. Okay, so you can check your high spin value also. You can check your low spin value also. In the low spin table, you can see in D6 low spin complex, it will be the most inert complex. So this most of the octahedral complexes proceeds through the square pyramidal intermediate or dissociative mechanism. So you need to remember these two tables. So here there is a comparison of tri-positive metal cations of the 3D series. Okay, and you can check here vanadium 3 plus, titanium 3 plus, iron 3 plus. In D2 complex or vanadium 3 plus, the change in CFAC it will be plus 1.14. So D2 you can check it will be plus 1.14, and in D1 it will be 0.57. You can see here 0.57. Okay, and Fe3 D5, Fe3 D5 low spin, this one it will be minus 0.86. So this is the order of a lability, or you can say this is the order of a inertness. So now tell me, out of these complexes seen in the screen, which one will be more inert complex? Out of these six complexes, which one will be the most inert complex? Can anyone say? So the negative value indicates about the inertness of the complex, and the positive value indicates about the lability of the complex. So the cobalt 3 D6 minus 4.0, this one will be the inert complex and this one will be the labile complex. If you compare these six examples particularly. Okay. Secondly, he is saying that if there will be isoelectronic metal cations present in a complex, isoelectronic means similar number of electrons, and here we will particularly discuss about the similar number of d electrons if present in between two metal complexes, which one will be labile, which one will be inert. You can see here chromium 3. When I am writing chromium 3, that means in the D cell there will be presence of 3 electrons. When I am writing vanadium 2 plus, also in the D cell there will be number of 3 electrons. So out of these two complexes, which one will be labile, which one will be inert in this case? He's saying that the lability of the complexes decreases with increasing charge on metal cation. So if charge amount it will be more on the metal cation, it will bind the other ligands along with the metal complex. It cannot perform the reaction in a faster way. So this more charged complex will be the inert one, and the less charged complex will be the labile one. So out of this complex, the chromium 3 plus will be the more inert comparating to the vanadium 2 plus. This one will be the labile one, this one will be the inert one. Similarly, you can see here iron 3 plus, manganese 2 plus. Here also D5 complex, here also D5 complex. But in iron, the charge amount is more. So this one will be the inert complex. And in manganese, the charge amount is less. This one will be the labile complex. Okay. And in similar way, we can say if the two or three types of D elements are present having the same electron, that means one metal from 3D series, another metal from the 4D series, another metal from 5D series. Which one will be labile and which one will be inert? So according to the CFE postulates, on going down the group, the inertness of the complex increases. If you go from 3D to 4D or 4D to 5D, the metal size will increases. If the metal size will increases, it can easily overlap the incoming ligands and it can form a stronger bond. So for performing of a reaction, the breaking of bond is necessary. The breaking of bond is necessary and the attachment of the incoming ligand is also necessary. So when the metal size will increases from 3D to 4D and 4D to 5D, these orbitals, it will make a better overlapping with the ligands and it will form a stronger bond. Then the metal ligand bond breaking, it will be difficult. So on going from 3D to 4D, 4D to 5D, the inertness of the complex will increases. You can see here example cobalt 3, rhodium 3, iridium 3 from 3D series, 4D and 5D. If I say which one of the complex will be more inert, then you can say the iridium complex because it comes from the 5D series. Here also you can see nickel, palladium, platinum. Okay, the platinum complex are the most inert complex out of these three complex. Will be the most inert complex because on going down the group the metal size will increases. When the metal size will increases, it can make a better overlapping with the incoming ligands or the persistent ligands or present ligands. That means here further metal ligand breaking, it will be very very difficult. Okay, so what types of other factors that can affect the inertness and lability of the complex? You can make a reading here also. So he's saying that in coordination number 4, comparing to coordination number 6, the substitution reactions, it can occur more easily. That means when there will be presence of coordination 4, number 4, definitely this coordination number 4 complexes are more labile comparing the coordination number 6. Because in coordination number 6, already 6 coordinate ligands are attached to the metal. It is already making a steric hindrance. In coordination number 4, the amount of steric hindrance is less. So the incoming ligand, it can easily interact with the metal complex and perform the reaction in a better rate or reaction rate. Okay. So when there will be presence of coordination number 4, there will be no doubt it will be a labile complex comparing to coordination number 6. If we will discuss about the main group elements, you can see here aluminum, silicon, phosphorus, sulfur. When the oxidation state will be higher, the complex will be the more inert. So you can see out of these four complex examples, this one will be more labile because the oxidation state is less. Here, the labileness will decreases because the oxidation state is 4. Here, the oxidation state is +6. That means this complex will be more inert. So when the oxidation state or the metal's positive charge will be more, it can bind ligands more strongly. That means further the bond breaking and the attachment of incoming ligand, it will be more difficult. Here also you can see a similar example: sodium, magnesium, and aluminium. In aluminium, the oxidation state is +3. That's why it will be more inert. It will be more labile. And in main group element also, strontium, calcium, and magnesium, you can see the lability of the complex increases in ionic radius with increase in ionic radius. This one will be the more labile complex, and this one will be the less labile complex. So you can just understood, or you can just calculate how to determine the lability and inertness of the complex of the main group of the transition element by using these two tables, particularly these two tables, or you can also predict the lability and inertness of the main group elements by using these three general concepts also. So this is all about the first part of the your topic, or the block 1 elements, block 1 part, the transition energy pathways and the reaction mechanism part, dissociative, associative, and interchange mechanism, and these are the energy steps or the bond breaking step and bond formation steps. You can see this reaction coordination is most necessary. You need to mention your exam book or notebook also. Okay, so further we will discuss about uh, the hydrolysis part. Okay, before going to hydrolysis, there will be some evidence that will support that most of the octahedral substitution reactions are uh, happening through the dissociative mechanism, not it will pass through the associative mechanism. These three evidence are: one will be the water exchange reaction, another will be ionization reaction, another will be the hydrolysis reactions. So first we will discuss about the water exchange reaction. So in water exchange reaction, we can see a metal complex. It will attach with the six water ligand. Then it will here the incoming ligand will be isotopically labeled water molecule. Why we are using isotopically labeled water molecule? If you are replacing one water ligand from the complex, then this isotopically labeled water it can enter into the complex. So you can easily identify. If the same water molecule is present, you cannot easily identify whether a same ligand will go outside or same ligand will enter inside. So make some differentiation. We are taking the isotopically labeled water. Okay, it will just replace one water molecule from the complex, and here the addition of the isotopically water ligand occurs. So now we will classify the metal atoms in which which types of metals atoms will do this type of water exchange reaction in a faster way, and which types of metal complexes will do the water exchange reaction in a slower way. Okay. So the classification, there are four types of classes: class 1, class 2, class 3, class 4 metals. So particularly the class 1 metals, it will make the water exchange in a faster rate, and the class 2 metals, it will make the water exchange in a slower rate. It will be very slow. It will just like behave just like a inert complex. So before going to the differentiation of class, we will first discuss about the general concept. This is called charge density. The charge density is nothing, but it is the ratio of charge divided by ionic radius. Okay. So if the charge density will be more, the metal, this metal can attach with these ligands more strongly. If the charge density will be more, then the exchange of this water molecule it will be very very difficult. It will be very very difficult. In which case, in that case, when the charge density will be more. So charge density is nothing but it's the ratio of charge divided by ionic radius. Okay, if the charge density will be more, that means metal and along with this water bond strength, it will be more. This replacement or substitution of this water molecule, it will be very, very difficult. So in which case, the charge density will be more. So the charge density means charge divided by ionic radius. So you can see the charge density will be high charge density, it will form when the charge amount will be high, otherwise the size of the metal atom it will be small. So in this case, particularly high charge and small size, in this case, the metal and water bond will be much more stronger, and this substitution it will be difficult. If the charge density amount will be less, charge density amount will be less, in which case, the opposite case, we can say the low charge and larger size. In this case, the charge density will be less, the water exchange will be faster. So particularly by considering this general concept, charge density, and other types of factors are also involved here. John Taylor distortion effect also, okay, and some thermodynamic stability factors. So we can classify these metals into four types: class 1, class 2, class 3, class 4. But by using charge density concept, you can classify you can classify the main group elements, which one will be labile and which one will be inert. So out of these four classes, class 1 will be rate of the class 1 metals, it will be faster. Okay. So the concept postulate is saying that The postulate states that the rate of exchange of water is very fast in case of class 1. And here you can see the rate of the reaction will be 10 to the power 8 second inverse. Okay. So the examples of class 1 metals are particularly the alkali metals and alkaline earth metals. So group 1 and group 2 particularly alkali and alkaline earth metals, and except beryllium, magnesium 2 plus, and particularly the chromium 2 plus and copper 2 plus. So you know from your graduation course that chromium and copper 2 they will they will a better example or good example of JTD, John Taylor distortion. So the structure which is already in a distorted form, it can easily participate in a reaction and give better product. So in class 1, chromium and copper and alkali metals and alkaline earth metals are included. Okay, so you need to remember these things: chromium 2 plus, copper 2 plus, and alkali metals and alkaline earth metals. In class 2, you can see the rate of exchange of water is fast, but slower than the class 1 metals. So class 1 rate of constant क्या what will be the rate constant of the class 1? 10 to the power 8. And here the rate of exchange rate will be in between 10 to the power 4 to 10 to the power 8. So within the class 2, we can include the dye-positive transition metals from the first row transition series, except V2 plus, which is slower than the chromium. That means you can include generally almost all the dye-positive transition metals, except the chromium 2 plus and copper 2 plus, because chromium 2 plus, copper 2 plus already we are included in the class 1 due to John Taylor distribution. Okay, and the trivalent lanthanides. So you need to remember these two general things: most of the dye-positive transition metals first transition series and the trivalent lanthanides. These two things. In class 3, again the rate of exchange water exchange is comparatively slower comparing to class 1 and class 2. Here the rate constant will be 1 to 10 to the power 4 second inverse. Second inverse means you can you usually understood that these are the dissociative mechanism. We are discussing about the dissociative mechanism or first order reactions. Okay. So in class 3, the examples are trivalent transition metal ions from the first transition series. In class 2, class 2, in class 2 we are considering dye-positive first two transition series. In class 3 we are considering trivalent transition metal ions. That means in class 3, if you are considering trivalent transition series, that means the charge amount will be more. When the charge amount will be more, the charge density will be more, the metal ligand bond strength will be more, and the rate constant and the rate of the chemical reaction it will be slower. Here the rate of the chemical reaction is 1 to 10 to the power 4. Here the rate of the chemical reaction is 10 to the power 4 to 10 to the power 8. You can see here. And in class 4, most of the inert complexes we are considering in class 4. Okay. You can see the rate of the reaction or rate constant value will be very, very less. So we can include most of the 4D and 5D metals in class 4. Okay, most of the rhodium, ruthenium, iridium, platinum 2 plus. Okay, and this is the order of the rate of water exchange. You can see in this order rate, you can see that chromium and copper 2, it will be always higher. The rate of water exchange will be higher in chromium and copper 2 plus, chromium 2 plus and copper due to John Taylor distortion. And in zinc 2 plus, it will be less, because here the CFSE, crystal field stabilization energy, will be 0 also. D10 complex, G2 plus, it will be D10 complex. Here also manganese 2 plus, that means this will be D5 complex. In D5 high spin complex also CFSE is 0. Okay, so in this order, if you go from this right side to left side, the CFS will be 0, then there will be little bit CFSE. That means the stabilization increases in the complex and the rate will be slower. And in on the opposite direction, the stability factor or the CFSE will be going towards the positive, and that's why the rate of water exchange it will be more. And this is the plus 3 series order or the tri-positive ions order. But out of the plus 2 and plus 3, definitely the plus 2 transition metals, it will show highest rate of the chemical reaction comparing to the plus 3. Okay. So water exchange is very, very important. Most of the entrance exams or semester also they will ask. Another reaction is the Anison reactions. You can see here in these reactions, an anion will replace the aqua complex. That means this is a metal hexacoordinated complex, and this anion X minus it will replace one of the water ligand from the complex. It will form a complex like that. Okay, and such types of reactions proceed either by dissociative and associative mechanism, but mostly it will proceed by the dissociative mechanism. In dissociative mechanism, initially one of the water will remove from the complex, it will form a pentacoordinated complex. Further, this incoming ligand it will attach with the pentacoordinated complex, then it will form a hexacoordinated or octahedral complex like that. So the incoming ligands it may be fluorine minus, SN minus, or CH3CO minus, and the rate constant order you can check here. That means out of these three incoming ligands in this particularly acetyl incoming ligand, the rate constant will be higher. The chemical rate of reaction will be higher. So these are the experimental data you need to remember. Further, the last step is that accretion reactions or hydrolysis reactions. So in accretion hydrolysis process, you are adding one water ligand, is a incoming ligand. It will replace a living group and it will attach with the complex. Here you can see. Here the incoming ligand is the water, but in Anderson reaction, the incoming ligand is not the water. Incoming ligand will be some halide complex or other types of ligands. It will replace one water molecule from the initial reacting complex. But in hydrolysis process, the incoming ligand, water will act just like an incoming ligand. It will remove one living group from the initial complex and it will attach with this particular complex. Okay, so when these types of hydrolysis process occur, if the pH will be less than 3, then it will told just like it is a acid hydrolysis. It will told just like a acid hydrolysis. If the pH is more than 8, then it will told just like it's a base hydrolysis. But in base hydrolysis, particularly we are using the OH minus ions. It will replace one living group from the complex, and the product complex will be just like that. Okay, if pH is neutral, we can say, or if pH is equal to 7, we can say this is just like a hydrolysis process, simple hydrolysis process. If pH is less than 3, we can say acid hydrolysis. It will be more than 8, it will be base hydrolysis. So first we will discuss about the acid hydrolysis of a complex. So in acid hydrolysis, the first step is that, first step you can see here, we are just taking a reacting complex. In the first step, just like SN1 mechanism, there will be removal of leaving group Cl minus. It will form a pentacoordinated complex. And in second step, there will be addition of water molecule and it will form a hexacoordinated or octahedral complex. So the rate determining step will be which one? The first one. So it will be first order reaction, or I can say this will be SN1 reaction. Okay. So here you can see we can express it like that. Rate will it will particularly depends upon Ka cobalt NH35X complex. That means initial complex. So there are some factors that affects the acid hydrolysis. One of the factor is the leaving group. Effect of the leaving group. So when the removal of the leaving group, it will be better. The reaction will be faster, and I can say the rate constant or the rate of the chemical reaction, it will be more, and the product amount will be also more. So when the rate constant amount will be less, I can say the rate of reaction will be slower. That means particularly the reaction or the hydrolysis process, it will depends upon a thermodynamic parameter or kinetic parameter. This is called Ka. Ka means the rate constant value. If the rate constant value will be slow, or low, or smaller, then the rate of the reaction will be also smaller. Okay. And the another factor is that the metal ligand bond strength. If the metal ligand bond strength will be more, then the performance of the reaction it will be very very less, because dissociative mechanisms particularly depends upon the breaking of the bond in between the metal and the living group. That means in initial step there will be a removal of chlorine ligand. That means it particularly depends upon the cobalt chlorine strength. If the cobalt chlorine strength will be more, then the process will be more slower. If the cobalt chlorine step will be weaker, or the bond in between cobalt and chlorine will be weaker, the reaction will be in a faster way. Okay. So the hydrolysis it will depends upon the bond strength in between metal and ligand, or I can say metal and the living group. So the metal ligand bond strength it will define by a thermodynamic parameter, or it is called equilibrium constant or capital K. And similarly, the rate of acid hydrolysis it will depends upon another factor. This is called Ka, small ka. The small ka is the kinetic factor. This is called rate constant. If the Ka value will be less or rate constant value will be less, then the rate of the reaction will be slower. Similarly, the metal bond strength it is also defined by another thermodynamic factor. This is called capital K or equilibrium strength. So if the capital K or equilibrium constant value will be more, then the metal bond strength will be more and the rate will be slower. So the small, so the Ka value it will favors towards the higher rate of reactions, and the more capital K value it will favor towards the slower rate of acid hydrolysis. So we can compare this kinetic value and this thermodynamic value in a linear equation, or we can represent in a graph also. So here we are representing this equation. This is called a kinetic equation. This k is a rate constant, and this RNS equation this is called P exponential factor A, and E activation energy R and T. This is kinetic equation. Here also another K. This is capital K. That means equilibrium constant. So we can correlate the kinetic equation along with a thermodynamic equation for different types of living groups. If we can consider different types of living groups, we can make a linear graph in between them. So the left side, this one will be, this axis will be representing log Ka, that means rate constant, and this will represent the equilibrium constant. And we are considering different types of living groups: NO3 minus, I minus, bromine minus, chlorine minus, chlorine minus. So these are the order of the different types of living groups. So out of this equation, we can see here in NO3 minus, the rate constant will be suppose -5, and the log K or capital K value will be -1. That means capital K value will be very very less. So when the capital K value will be less, that means metal and ligand bond strength is less, and this will perform, the reaction will perform in a faster way. That means the decomposition of or removal of NO3 minus ion or X ion from the cobalt complex, it will be occur in more easier way. And here also we can see -10, -9, -8, -6, here -4. So -4 comparing to -9 and -10 is a larger value. That means it is a little bit larger rate constant value or a lower equilibrium constant value. If you discuss about the NO3 minus, it is a lower capital K value and it is a larger rate constant value. That means the decomposition of NO3 it will be more favorable from this complex. So here is predicting the order from the graph. It has been observed that the reactivity of X minus group decreases in the order. That means in NO3 minus case, the reactivity will be more. That means it can easily remove from the complex cobalt NH35 NO3 minus, and it can perform acid hydrolysis or base hydrolysis in a faster way, particularly acid hydrolysis. So the figure shows that the stronger the ML bond, slower is the rate of acquisition. or acid hydrolysis. That means the rate of the process or the acquisition process or hydrolysis process particularly depends upon the breaking of ML bond. Breaking of ML bond. That means when the breaking of ML bond will be easier, then the rate will be more. When the ML bond breaking is less easier, the rate will be less. Okay. So this evidence supports that the hydrolysis process, particularly the acid hydrolysis process, proceed by dissociative mechanism or SN1 mechanism. Okay, you can see the picture here also. This is rate constant. This is equilibrium constant. And when I'm saying NO3 minus, if I'm saying NCS minus, here also you can say the log K value will be more positive. When the log K value will be capital value will be more positive, that means metal and ligand bond strength is stronger. That means the decomposition will be very very difficult. Along with we can predict also here -9. The rate constant value will be -9. -9 means the rate constant will be very very slow, or the rate constant value will be very very smaller. That means the rate of reaction will be also very very slow. Okay, but if you compare NO3 minus here, the capital K value will be less. That means metal ligand constant is less, and the rate constant value it will be more comparing these values. Okay, so this plot is called linear free energy relationship. This is very very important. So if you can follow the ignomaterials or in ignomaterials, you can also discuss or you can also carefully make a note on the terminal questions. In terminal questions, if the material it is mentioned that linear free energy relationship this one. Okay, or in material in initial page of your study material you can get this picture, linear free energy relationship. This is much more important. Okay, so there are several factors that also affects the acquisition process or hydrolysis process. The first factor will be the charge effect. So postulate is predicting that the higher the positive charge on the complex cation makes the bond breaking between the metal and ligand more difficult. You can check this reaction directly. So in this complex, the charge amount is 2 plus, or in this complex, the charge amount is plus. Okay, so out of this two complex, in which complex the charge amount will be more? This one. So saying that the higher positive charge complex cation makes the bond breaking between the metal and ligand will be more difficult. That means when the charge amount will be more, then the breaking in between cobalt and chlorine will be more difficult. In this case, the rate constant value, or I can say the rate of chemical reaction, it will be slower. But when the charge of the complex, it will be lower, +1. Here, in between cobalt and chlorine, the bond will be little bit weaker when the charge amount will be less. So in this case, the cobalt chlorine bond breaking, it will be more easy. Then incoming ligand water, it can attach to the complex more easily. Okay, here also you can check the rate of the reaction will be higher. K value will be higher. Okay, so another factor is the chelation factor. In chelation factor, he's saying that you can take two types of complex. One will be chelated complex, another will be non-chelated complex. Chelated complex, how can I identify the chelated complex? When there will be a chelating ligand, ethylene diamine here. You can there is presence of two numbers of En compound or En ligand or ethylene diamine. You can say here that this one will be chelated complex, this one will be non-chelated complex. So you can take two examples. One will be chelated, this one will be chelated complex example, this one will be non-chelated complex. So in these two complex, the charge amount is similar. So you cannot differentiate in which cases the rate will be faster or rate will be slower. So it's saying that in chelated complex, the rate will be slower because in chelated complex, the attraction in between the chelating complex along with the water, it will be very, very weaker. When there will be presence of chelating complex inside the inside a complex, coordination complex, there will be less attraction in between this metal along with the incoming ligand. So the rate of the reaction will be lower or slower, little bit slower. But in this complex, there will be no presence of chelating complex. The attraction in between the incoming ligand or water molecule along with the cobalt, it will be higher. So this reaction will be occur in a faster way, and this reaction it will be occur comparatively to little bit slower way. You can read out here. It is seen that intermediate obtained from the chelated complex is larger in size than that of intermediate obtained in the non-chelated complex. There is less attraction between the larger intermediate. Larger intermediate means is saying that about the chelating complex and water molecules. There is less attraction in between larger intermediate and water molecules than the smaller intermediate and water molecules. Thus, a chelated complex undergoes accretion at a slower rate than the non-chelated complex. Okay. So here also accretion process occurs. Here also accretion process occurs by going through dissociative mechanism. In first case, leaving group removes, and in the second case, the incoming ligand attached to the initial complex. Here also similar way. In first step, the income in the leaving group removes from the complex. In second step, the water molecule will attach to the initial reactant, and it will forming the complex like that. Yes or no? But out of these two steps, which one will be faster, which one will be slower? This one will be faster, the non-chelated one. The chelated one will be the slower. Second thing, another factor is that steric hindrance. He's saying that if along with the EN groups or if along with the chelating groups, some other side groups are present or other steric groups are present, just like alkyl groups, CH3, C2H5, then the ligands becomes more bulky. When the ligands becomes more bulky, then it observed that it will possesses more steric hindrance. And if the steric hindrance inside the reacting complex, it will be more, then it will be favor to the dissociative mechanism. Because in dissociative mechanism, in first step, there will be removal of the leaving group. There will be removal of the leaving group. If in initial complex, or if in the spectator ligands, more will be the steric or bulky groups, then it will easily repel this leaving group from the complex. So that means steric hindrance presence initially in the reacting complex, it will favor the dissociative mechanism. It will favor to the dissociative mechanism. That means it will help to remove the leaving group from the complex. Yes or no? So he's saying that in initial complex, if the steric groups are present, then the dissociative dissociation will be easy and the rate of reaction will be faster. Okay, if the bulky group CH3, C2H5 are present along with the EN group, then the reaction will be faster. Ethylene diamine in reaction, ethylene diamine, suppose we can draw like that. NH2, here also NH2. Is saying that the postulate saying that in this point, in this carbon point, carbon skeleton, if there will be presence of any bulky group means you can just add CH3 groups, C2H5 groups, then the steric hindrance of the overall group will increases. If you can compare this ligand and also you can compare this similarly this ligand. Similarly, you can write here NH2, NH2. So in out of these two ligands, if in a complex this ligand is present or in another complex this ligand is present, then in this case the rate of accretion will be faster due to the presence of this steric group, because the steric groups it will repel the negative ligands, repel the leaving group ligands from the complex more easily. So the presence of the steric groups In the initial reactant complex, it will support the dissociative mechanism. It will support dissociative mechanism. So the steric hindrance, it will be good for the dissociative mechanism or SN1 mechanism. Another important thing is that base hydrolysis. So in base hydrolysis, you can replace one leaving group from the reacting complex and you can add one OH minus group to the complex. So you can see here, this is the initial reactant cobalt NH35Cl2 plus and the final product is cobalt NH35OH2 plus. That means removal of a chlorine group from the complex and the addition of a OH group to the complex. Okay, so you can see here, there are three steps. First step, second step, third step. So in first step, this is the equilibrium process. That means the forward backward reaction can go simultaneously. Yes or no? And so in first step, the OH minus, it will abstract a proton from one of the any ammonia. There are 5 amine group ligands are present inside the complex. Out of this 5 amine ligand, the OH minus, it can abstract one proton out of this 5 complex or 5 amine complex, any one. So here the complex will form cobalt NH34 NH2 minus Cl, and the overall charge will be plus, and it will be along with a water ligand. In second step, there will be removal of the leaving group. That means Cl minus group. It will form the complex like that. That means this one will be the rate determining step. This step will be the rate determining step. Second step. And in third step, this complex, it will attach with a one water ligand, and out of this one water ligand, one H plus ion, it will abstract by NH2 minus ion and OH minus ion, it will retain inside the complex like that. So in base hydrolysis, three steps are proceed one by one. First step will be the first step, and the second one will be the slowest step, and the last one will be the fastest step. And this middle one will be the rate determining step. So you can easily write the rate constant will be that the rate, it will be multiplied by rate Kb, it will be multiplied by this complex. Okay, you can write simply. Okay, if you calculate one by one, what will be the rate constant of this step? The rate constant of this step will be the K. It will be multiplied this initial concentration and multiplied by the OH minus concentration. So in the first step, you can represent by the rate constant. This one. K, it will be multiplied by conjugate base and water. Then it will be cobalt NH35Cl minus OH minus. You can see here. This will be the conjugate base. This one. After the abstraction of proton, this reacting complex will be the conjugate base. This will be the water. This will be the initial reactant complex, and this will be the OH minus. So the equilibrium constant will be the product of these two concentration divided by product of these two concentration. You just represent like that, and you can modify this equation. You can put conjugate part base one part, and you can shift it. You can shift these two parts to another side. The equation will be just like that. But according to chemical kinetics, you know the rate will be K into Cp. K will be Cp means conjugated base. K multiplied Cp, this part. This part will be the conjugated base. Kb multiplied by Cp, this part. So in place of Cp, you can write this expression particularly. We are here using this SSB complex or steady state Aptos complex. So in place of conjugate base, you can put this amount. Then the chemical rate reaction will be like that. And the rate will be Kp, cobalt NH35, Cl2 plus OH minus. Okay. So in conjugate base mechanism or base hydrolysis mechanism, it follows dissociative path, but it seems to be second order reaction. That means the rate it will depends particularly on the conjugated base concentration also, along with the OH minus concentration also. Here you can read out the base hydrolysis proceeds by the SN1 mechanism, but it is consistent with the second order and first order with respect to the reacting complex and first order with respect to the base. So in acid hydrolysis, we can say it is first order and it follows the SN1 mechanism. But in base hydrolysis, it follows the dissociative mechanism, but the rate expression will be the second order. That means it is first order along with respect to the initial concentration. Also, it is first order with respect to the concentration of base. So in base hydrolysis, what is the need of abstraction of proton in the first step? First step is proton abstraction. What is the need of the abstraction of proton in the first step? So after the abstraction of proton in the first step, it will form a NH2 complex. NH2 means NH2 minus. When it will be NH3, it will be just like a neutral complex. Now it is NH2 minus. When NH2 minus complex will present, now it can act as a pi donor ligand. Simply I can say NH3 is a sigma donor ligand. If I say NH2 minus, then it is a pi donor ligand. That means the nucleophilicity of the ligand will increases. This NH2 minus ligand, it will donate a pair of electrons towards the metal complex to form a pi bond. When the electron density of the cobalt complex will increases after the donation of the electrons from the NH2 minus, then it will repel the electron density of the chlorine or leaving group. Then the chlorine, it will dissociates from this complex. It will form a product complex like that. That means the formation of NH2 minus complex, it will make favorable for the removal of chlorine. But in acid hydrolysis, these types of processes doesn't occur. That's why in comparing to the acid hydrolysis, base hydrolysis, the rate of base hydrolysis is million times faster than the acid hydrolysis. So always remember Kb it will be more than the Ka. That means the rate of base hydrolysis it will be always faster than the Ka. What is the reason? First reason is that in base hydrolysis, initially the abstraction of proton occurs. After the abstraction of proton, there will be a formation of pi donor ligands, just like NH2 minus ligand. And this NH2 minus ligand, it will form a pi bond along with the metal complex. After the formation of pi bond along with the metal complex, the electron density of the metal, it will increases. It will repel the chlorine or leaving group from the reacting complex, and the chlorine will easily remove from the complex. Second thing, you can also check also the charge effect. Charge effect means you can see here in base hydrolysis, if you consider the rate expression, this will be Kb this complex, conjugate base complex. Here the charge is plus 1. Here the charge is plus 1. But in acid hydrolysis, you can consider this one. Here the charge is 2 plus. Then tell me, in which case the rate will be faster? In one case, the complex charge is 2 plus. In another case, the complex charge is plus 1. So definitely, when the charge amount will be less, the reaction rate will be faster. That's why in base hydrolysis, the Kb amount will be more. These are two to three examples, regions we are expressing here for the faster amount of the base hydrolysis comparing to the acid hydrolysis. Yes or no? And the another factor is that this chlorine position and the pi donor ligand position, it must be anti-periplanar position. That means it must make a 180-degree to each other, just like cis position. This one NH3 position, this another NH3 position, or NH3 position, this chlorine position. This needs to make anti-periplanar position for removal of the leaving group. If it is present in anti-periplanar position, then the cobalt chlorine's anti-bonding sigma orbital, it will available in the direction of the NH2 position. This will be available in this direction. So it can easily, NH2 minus, it can easily donate its electron towards to the anti-bonding orbital of cobalt Cl. When it donates its electron towards the anti-bonding orbital of cobalt Cl, then definitely there will be breaking of the sigma bond. Because after the donation of electron to a sigma star orbital, the bond order will decreases. Okay, here we will discuss some few another examples. You can see here, this is one complex. We are taking one hexacoordinated complex. In the first step, in the equilibrium step, there will be abstraction of proton occurs. Abstraction of proton means, and there will be OH minus ion. This will abstract one H plus ion. It will abstract one H plus ion from this position. Now this complex is NH2. Okay, and in third step, this NH2. In third step is the slowest step. There will be removal of leaving group. Okay, chlorine removal occurs. It will form a pentacoordinated complex. So you can see here, out of this all five ammonia amine complex, it will abstract the proton from this amine complex, which is transposition or anti-periplanar position to the leaving group. It will abstract the proton from this NH3 group because the NH3 group, it is present transposition of the leaving group. Then it can easily donate its pi electron towards this cobalt complex, and there will be a breaking of cobalt Cl bond like that. So always the proton abstraction occurs from the anti-periplanar position of the leaving group. Then the reaction will be faster. Same process, same steps here. In the first steps, proton abstraction occurs. There will be a formation of conjugate base. In the next step, there will be removal of leaving group. There will form a pentacoordinated step. And the another step, there will be addition of water ligand or incoming ligand. It will form a hexacoordinated complex or octahedral complex like that. But the proton abstraction is the most important factor in base hydrolysis. It occurs always from the opposite position of the leaving group. If in this position there will be no presence of proton, then it can abstract proton here also, here also, here also. But in this case, the rate will be slower. The rate will be slower. Okay. We can also see here the example of some of the complex is telling that in the rate of, if you compare the rate of base hydrolysis of cobalt En2Cl2 plus 1 is faster, whereas the rate of base hydrolysis of cobalt En2NO2Cl or En2CnCl, it will be slower than the this ones. So he's saying that this complex showing base hydrolysis faster, and these two complexes showing the base hydrolysis in a slower rate. What is the reason behind that? Okay, here the spectator ligands or particularly the non-living group ligands are the NH2, CH2, CH2, NH2. That means when there will be abstraction of proton occurs, particularly from the NH2, then this NH2, it will donate its electron towards the metal direction to form a pi bond with the metal. Then the living group will remove from the complex. But in these two complex, particularly, the electron withdrawing groups are present, NO2 Cn minus. But here electron withdrawing group is not present. So when NH2 minus donates its electron towards the metal direction, the NO2 minus, it will abstract or receives this electron density towards itself. NO2 minus कौन करेगा ना से जो cobalt metal होगा जो electron density थी वो ता कौन करे नीचे आड़ को abstract करना होगा. So when it will abstract the electron density towards itself, then the electron overall electron density on the metal complex, it will decreases. Then it cannot easily repel the leaving groups. But here there will be no presence of the NO2 minus group, electron withdrawing group. That means the electron density coming from the NH2 group, it will located on the cobalt complex in this complex. cobalt En to Cl. So that's why in this complex, the cobalt electron density it will repel to the chloride group. Then easily dissociation can occur easily. But in these two complex, the two electron withdrawing groups are present, NO2 minus and Cn minus. It can abstract the electron density accumulated on the cobalt metal. So cobalt metal over जो electron density थी वो NO2 minus Cn minus कौन करूँ निजे abstract करना हो. पर तले electron density cobalt ऊपर कौन हिजो कमी जुबा. Then कौन होगा ना से chlorine को कौन करेगा जितनी amount repel करिए लगता से easily repel कर परिवो ना. Okay. So similarly, if you compare this complex and this complex, out of these two complex, NO2 minus and Cn minus, NO2 minus electron withdrawing tendency is more comparing to the Cn minus. Okay. If he gives the order of make a arrange a order of the base hydrolysis of this one, this one, this one, then which complex can show better base hydrolysis? This one. This one will be the first one. This can show in a faster way the base hydrolysis, and the second preference will be this one, and third preference will be this one. So when electron withdrawing groups present inside the complex, it can abstract the electron density from the metal. When the electron density of the metal decreases, it cannot easily repel the leaving group to remove from the complex. That's why when the electron withdrawing groups are present inside the complex, the rate will be slower. Okay, this is another example of two other complexes of the same complex. These are two isomers. This is called red isomer. This is called purple isomer. In the cobalt attached with a triene complex. Triene complex means it's a tetracoordinated complex. NH2, CH2, CH2, and CH2, CH2, NH2. Triene means three ethylene groups are present. CH2, CH2 groups. Here also CH2, CH2 groups. Here also CH2, CH2 groups. That's a triene. Triene. That is a tetracoordinated complex. Triene ligand. This is a tetracoordinated complex. This is a tetracoordinated ligand. TREN. 1, 2, 3, 4. Yes, sir. And along with its tetracoordinated ligand, there will be two monodental ligand, NH3 and CS. Okay. Based on the two complexes, red isomer and the purple isomer. Is asking that out of these two isomers, which can show better hydrolysis or which can show in a faster way the base hydrolysis. First one or second one. So the red isomer it will show the better in better way or in a better rate the base hydrolysis compared to the purple isomer because in the red isomer in the opposite position of chlorine there will be presence of NH2. On the NH2 the abstraction of proton it can easily occur because in on nitrogen along with nitrogen hydrogen is also present. So here we can easily abstract the protons. But in this complex, on this opposite direction of chlorine, here we can see here on the nitrogen, there will be no presence of hydrogen. So the abstraction of hydrogen cannot occur here. So here the abstraction of hydrogen occur from any other four places. Okay. So out of these two complexes, it can show the base hydrolysis in a faster rate because a fast step, which one is the step one abstraction of proton, that can occur from this way. When the abstraction of proton occur from this position, then the nitrogen electron density it will shift towards the cobalt, and the cobalt will repel this chlorine. It will easily remove from the complex. You can see here. In the first step, the abstraction of proton occurs from this position NH2. Now it will be NH, and the nitrogen electron density will shift towards the cobalt, or nitrogen lone pair electron it will donate towards the cobalt. Then it can easily remove the chlorine, and the complex will be like that. Thereafter, there will be attachment of the incoming ligand, water, and from the water, the H plus will be abstracted again to the NH position, and the OH will be attached to this position. But in another complex, the proton abstraction occurs from here, because here there will be no presence of hydrogen. Then in next step, the chlorine will be removed from the complex, Then another step, the water will attack. So if the water will attack, they can attack in two direction, in this direction also, in this direction also. So mostly this complex will fall. It will attack from the below position, below the plane, because there is less steric crowding below the plane. So it can easily attack to the below the plane. So this amount will be 85%. But the rate of the reaction of this complex, it will be faster comparing to this one. Because on the opposite of the leaving group, there is a presence of ligand. In this ligand, there will be protons are present. So the proton abstraction, it will be occur here easily. Okay, you can check also. Therefore, the rate of base catalyzed hydrolysis of the red isomer, that means this one, red isomer, cobalt triene NH3. It is much faster. Okay, so this is red isomer, this is purple isomer. Okay, thank you. You can also ask any doubt if you have any doubt also. So in today's class, we'll complete 2 units of block 1. First unit, second unit. So if you have any doubt, you can ask also.
Sir, tomorrow we'll ask about it. We have not studied it till
Oh,
now.
okay. You can collect the study material from course site also, unit 1 and unit 2. Okay.
Okay, sir. And in assignments also we have some doubts. Can we ask it tomorrow?
Okay, regarding which topic? This theoretical topic.
Yes, sir.
Okay, now, or other some practical topics.
No, sir. Theoretical.
Okay, you can ask.
Okay, sir.
Hello, hello, hello. Chemistry ignore କଣ ସେମିତି କଣ unofficial group ଅଛି କି? Group ଅଛି ବୋଲେ ମତେ ଟିକେ add କରିଦିଅ। Hello.